So these are our goals today, these 3 problems. And if we get past them, so be it. If we don't, then that will be the journey. But let's start by removing the image from our field of view and get to a blank surface. This picture in number 9 that you're looking at that looks so scary is actually a composition of very simple geometric constructions. Let me explain what I mean. And to explain this, I'll need a compass and a protractor and pencils that are very precise. And I'll also need to dim the lights so when I construct these things, you can actually see them. So the lights are going to get dimmer here on the video so that you can see the faint drawings that I'll make with these pencils and compasses. So let's start building the figure that we saw in number 9. And now you see that we have 2 parallel lines. These lines, being parallel, offer us some important properties that we need to be aware of. For example, if we look at figure 9, there is a line that cuts across the image diagonally about like this. It goes from here to here. This line is called a transversal. 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 And when we have a transversal, you will see the shape of either a Z or a Z that has been flipped. So here we see a Z that has been flipped. And there is a rule or a theorem in geometry called the alternate interior angles theorem that says that these angles right here, this angle here, and this angle here, are equal to one another. That's called the alternate interior angles theorem. If 2 parallel lines are cut by a transversal, then the alternate interior angles are equal. So let's finish building our image. There was, in fact, another line that cut these parallel lines about like this. This is also another transversal. We see a Z shape here, and the corner spaces of that Z shape are alternate interior angles. So just as these 2 angles are equal by the alternate interior angles theorem, these 2 angles are also equal. So let us now label this image with all the things that came with it in the problem. We were told that this top line should be called L, and this bottom line should be called M. We were given that this angle right here was called angle 1. This angle over here was called angle 3. This angle inside the triangle here, it was called angle 2. This angle over here was called angle 4. And this angle was called angle 5. Further, we were given that this angle right here was 73 degrees, and we were given that this angle right here was 49 degrees. This looks like the shape given to us in number 9. So now that we have this theory, this working model of what is happening, we can analyze the picture without fear, and we can immediately see what some of the answers are. By the alternate interior angles theorem, angle 1 is equal to 73 degrees. Here is the picture. Angle 1 has to be equivalent to 73 degrees by the alternate interior angles theorem. Alternate interior angles theorem. Angle 1 is 73 degrees. There's no measurement involved. It's a theorem. We assume it to be true. Further, we have this backward Z shape. If this is 49 degrees, then angle 4 by the alternate interior angles theorem must also be 49 degrees. So angle 4 by the alternate interior angles theorem must be 49 degrees. We'll label it. We'll label angle 1 73 degrees. And we'll label angle 4 49 degrees. Now, to solve for angle 2, we can do one of two things. We could notice that if I add 73 and 49 together and subtract from 180, I will get angle 2. Alternatively, we can use the triangle angle sum theorem and add the interior angles of the triangle that we have, 73 and 49, and subtract from 180, and we will get angle 2. Notice that both operations are identical. We add up these angles and we subtract from 180. So by whatever measure you use, you will arrive at the correct answer. So let's do that. Down here in our side work area, let's add 73 and 49. Three plus 9 is 12. Carry the 1. 7 plus 4 is 11, plus 1 is 12. These two add to 122, and we simply take 122 from 180. Here we have to borrow from the 8. It becomes a 7, and we make the 0 a 10. And take 2 from 10, and we get 8. And 2 from 7, and we get 5. 1 minus 1 is 0. So, by the triangle angle sum theorem, we have found that angle 2 is 58 degrees. Let's go back to our paper. Angle 2 is 58 degrees. And we prove that by the triangle angle sum theorem, TAST. And we see that all that's left is angle 3 and angle 5. So, notice that angle 3 forms a linear pair with 73 degrees. That means that the two angles have to add to be 180 degrees. Since if you join them together, you have a half circle, which is 180 degrees. So we need only to subtract 73 from 180 to get angle 3. 180 minus 73. We borrow from the 8 and make it a 7, and make the 0 a 10. 3 from 10 is 7, 7 from 7 is 0, and 1 comes down here. This is called the supplementary angles theorem. These angles are supplementary because they add to 180. So angle 3 is 107 degrees. And that was the supplementary angle theorem. Angle 3 is 107 degrees. Now to angle 5. Angle 5 forms a linear pair with angle 4. And by the alternate interior angles theorem, we proved that angle 4 was 49 degrees. So if we subtract 49 from 180, we'll have angle 5 by the supplementary angle theorem. 180 minus 49. We'll borrow. 9 from 10 is 1. 4 from 7 is 3. And we bring down the 1. So by the alternate interior angles theorem and the supplementary angles theorem, we find that angle 5 is 131 degrees. We'll do supplementary angle theorem here. And we saw that angle 5 was 131 degrees. There's almost no need to consult the key since we built the image. And from that image, we applied some theorems, and we were able to find the answer to a certainty. That logic that we just used here is going to be at work in number 10 and number 11. Number 10 is composed of 4 parallel lines cut by 1 transversal. That's how you can think of this box as 4 parallel lines. Here's a pair of parallel lines, and here's a pair of parallel lines. This diagonal line is the transversal that cuts these parallel lines here, and it also cuts these parallel lines here. So let's see if we can work through this image. We might need to draw it bigger, but we might be able to work through it this way. Now, there is another indicator here that we need to notice. All of these angles are right angles in the corners of the rectangle. It forms a complementary relationship with 52 degrees. So angle 6 and 52 degrees must add to be 90 degrees. This is plain to see. This is a right angle. A right angle is 90 degrees. We have a transversal cutting it, and so this angle 52 plus angle 6 must be 90 degrees. So this is the complementary angles theorem. So if we go to our work surface, here we don't need this picture anymore. If we go to our work surface and we subtract 52 from 90, we'll have angle 6. 9 becomes 8, 0 becomes 10. 2 from 10 is 8, 5 from 8 is 3. So by the complementary angles theorem, angle 6 is 38 degrees. Okay. We now know that angle 6 is 38 degrees. What else do we know? In the other corner here, we have angle 2 and angle 3. We know what these angles are by the alternate interior angles theorem. If we look at the shape, we see a Z shape here. You see that? So that means, let me use a different color here. That means that whatever angle 2 is, it is equal to 52 degrees because of the alternate interior angles theorem. This is two parallel lines cut by a transversal. So angle 2 has to be equal to 52 degrees. So by the alternate interior angles theorem, angle 2 is 52 degrees. What else do we know? Well, if we look at this shape in a different way, let me turn the shape here. We see another Z shape. This one is the flipped Z. Here I have two parallel lines cut by this transversal. So I can trace this backward Z shape, and the corners of the Z shape by the alternate interior angles theorem have to be the same. So that means that angle 3 is equivalent to angle 6. And angle 6 was 38 degrees by the complementary angles theorem. So by the alternate interior angles theorem, we can prove that angle 3 is also 38 degrees. And this was by the alternate interior angles theorem. So what about angle 1, angle 4, and angle 5? I should write that angle 2 is 52 degrees. Okay. We can solve for angle 5 using the triangle angle sum theorem, and we can solve for angle 1 by using the complementary angles theorem, and then we can solve for angle 4 by using the triangle angle sum theorem. That was moving a little bit too fast. So looking at this triangle right here, I have two of the interior angles, and by the triangle angle sum theorem, I know that all three have to add to 180. So by the triangle angle sum theorem, if I add 38 and 86 and subtract from 180, I'll get angle 5. Over here in side work, we will add 38 to 86. 8 plus 6 is 14, carry the 1. 3 plus 8 is 11, plus 1 is 12. So these two angles add to 124 degrees. And if I take them from 180, by the triangle angle sum theorem, I'll have angle 5. So we'll have to borrow from the 8, make it a 7, turn the 0 to a 10. 4 from 10 is 6, 2 from 7 is 5, and 1 from 1 is 0. So by the triangle angle sum theorem, angle 5 is 56 degrees. Triangle angle sum theorem. Triangle angle sum theorem. Angle 5 is 56 degrees. What about angle 1? Well, as we said before, we have a right angle that is cut here, not by a transversal, but it's cut nonetheless. and it forms a complementary relationship. So that means that angle 1 and angle 5 have to add to 90. And by the triangle angle sum theorem, we saw that angle 5 was 56 degrees. So 90 minus 56 will give us angle 1. (90 minus 56). This is the complementary angles. We'll borrow here. 6 from 10 is 4. 5 from 8 is 3. So by the complementary angles theorem, angle 1 is 34 degrees. Complementary angles theorem, angle 1 is 34 degrees. Now all that's left is angle 4. And as I said, we would need to use the triangle angle sum theorem to prove what angle 4 was. Triangle angle sum says that if we add up all the interior angles of the triangle, it's 180. So 34 plus 52, if we add those together and take that from 180, we'll have angle 4. So let's go and add 34 to 52. Four plus 2 is 6. 3 plus 5 is 8. So we have 86 degrees as the sum of those two interior angles of that small triangle. And we just need to take that from 180. Okay. 6 from 10 is 4. 8 from 17 is 9. So, by the triangle angle sum theorem, the measure of angle 4 is 94 degrees. And we've completed the image. Notice that we had to solve it in those steps, and we had to pay careful attention to the alternate interior angles. We had to understand parallel lines. We had to recall the complementary angles theorem and the triangle angle sum theorem. A lot of mental baggage boarded the plane with this problem. Now, all the mental baggage from number 9 and number 10 will need to be brought to bear on number 11. And number 11 is one that we'll need to draw. It's too small. So sit back for just a moment, and we'll try to construct angle 11 as best we can. This top part was rather small in number 11. Let's define the edges of it right here. And also we'll use that point again right there. There was a transversal cutting these two parallel lines going diagonally about like this, almost like the way I drew that line before. We'll connect the end of this down here like this. Further, there was another transversal cutting this way. So before I draw that transversal, let's talk a little bit about what we're doing. We have this shape. Do you see how it looks like a Z? Do you see that? So before we draw in the rest, this is what I meant about building the image will actually help you. We know that by the alternate interior angles theorem, this angle is equivalent to this angle. Now, just so you have a point of reference, on the paper, this angle was labeled 1, And this angle down here was labeled 8. Okay? So we don't know what either angle is, but once we do find one of them, we'll have the other by the alternate interior angles theorem. And it was only by building the image, kind of stripping away all the stuff that's in number 11 and starting from a simple blank page, that we're able to see that really instantly. So now we'll put in that other transversal. This one was bigger, like this, or longer. Kind of like that, right? So that's a transversal. And before we get anything else drawn on the page, let's notice that we now have a backward Z shape. So whatever this angle is here, by the alternate interior angles theorem, that must be equal to this angle here. These are the corner spaces of these Z's and backward Z's, alternate interior angles. And on the shape, this angle here was actually given to us as 47 degrees. And this angle down here was labeled as angle 7. So we've already solved one of them. We've solved angle 7 by the alternate interior angles theorem. Angle 7 must be 47 degrees. Okay, let's finish drawing our shape before we do too much more. So now all we have to do is connect the edges of the shape, or the vertices here. And the vertices here, and we'll erase the extra markings. Okay, it doesn't look exactly like the picture drawn, but it's the same idea. So if you put a protractor to the picture I just drew, it would not match the shape. But all of the relationships and the theorems that would apply to prove those relationships are the same. So what we're going to do here is understand that this shape is not entirely perfectly representative of the measurements, but that all of the relationships are the same as the picture that you have. It shows us in the image that these two lines are parallel. These little triangles indicate that parallel relationship. Okay, what else were we given? Let's start labeling the picture. We were given here that this angle was 42 degrees, and that this angle was 71 degrees, and that this angle over here was 36 degrees. The rest of these we have to find. This is angle 4. This is angle 2. This is angle 3. This is angle 5. This is angle 6. I think I've labeled everything. Now I can turn the lights back up. You see the shape looks pretty good, right? We've gotten rid of all those extra marks, and we can work with this shape. More human-sized. Okay, so what else can we determine from this shape? There are no more alternate interior angles, just so you know, but we can label the angle that we found. Let's label the angle that we found. We found that angle 7 was 47 degrees. So let's go back here and label angle 7, 47 degrees. And that was by the alternate interior angles theorem. Alternate interior angles theorem. Remember what that was. If two parallel lines are cut by a transversal, then the alternate interior angles are equal. So that's how we prove that for number 7. Okay, let's go back to the picture. We have, in the middle of this picture, vertical angles. Angle 2 is vertical angle with angle 71. So by the vertical angles theorem, angle 2 is 71 degrees. We can mark that. Angle 2 by the vertical angles theorem is 71 degrees. Remember, vertical angle says if two angles are vertical to one another or opposite one another like this, they are equal. And notice also that angles 3 and 5 have a vertical angle relationship. If I turn the page, you see that they're opposite of one another. Okay? So even though they're across from one another, we still call it vertical angles theorem. And we'll find that here momentarily. So how will we find angles 3 and 5? Well, we only need to find one because they're equal to one another. How would we find angle 5? Well, angles 2 and 5 form a linear pair with one another. Okay, they're cut by this line. So they are supplementary. That means they add up to 180. So down here in side work, we simply need to subtract 71 from 180, and we'll have angle 5, which means by vertical angles, we'll have angle 3 as well. So we just need to subtract 71 from 180. We'll borrow from the 8 and make it a 7. Turn the 0 into a 10. 1 from 10 is 9. 7 from 7 is 0. And 1 comes down. So, by the supplementary angles theorem, angle 5 is 109 degrees. And by the vertical angles theorem, angle 3 is also 109 degrees. So, let's label angle 5. We'll say that we use the supplementary angles theorem, and we found that angle 5 was 109 degrees. And by the vertical angles theorem, angle 3 was also 109 degrees. And you see that this shape and all of its frightening complexity is starting to collapse into simplicity. We only have a few more angles to solve for. So what's missing? Angle 1 is missing, and we can use the triangle angle sum theorem to find angle 1. If we add 47 and 71 and subtract that sum from 180, we'll have angle 1 by the triangle angle sum theorem. So let's first add 47 and 71. Seven plus 1 is 8, and 4 plus 7 is 11. Okay, so now we take 118 away from 180. We borrow from the 8, turn it to a 7, make the 0 a 10. 8 from 10 is 2. 1 from 7 is 6. So, by the triangle angle sum theorem, angle 1 is 62 degrees. Let's go label that. Angle 1 is 62 degrees by the triangle angle sum theorem. Okay, we found that. Let's look at angle 4. We can apply the triangle angle sum theorem to angle 4 as well. We have here this scalene triangle. See that? It will have no congruent angles. If we add, according to the triangle angle sum theorem, 109 to 36 and subtract that sum from 180, we'll have angle 4 by the triangle angle sum theorem. So let's do that in side work. Let's add 109 to 36. Nine plus 6 is 15. Carry the 1. 0 plus 3 plus 1 is 4. And we bring down the 1. So they add to 145 degrees. And if we take that from 180, we'll have angle 4 by the triangle angle sum theorem. First, let's borrow from the 8, make it a 7, make the 0 a 10. 5 from 10 is 5. 4 from 7 is 3. And 1 from 1 is 0. So, by the triangle angle sum theorem, angle 4 is 35 degrees. By the triangle angle sum theorem, angle 4 is 35 degrees. 2 left. Angle 6 and angle 8 are all that remain, and both will be solved using the triangle angle sum theorem. Do you see that? We have 2 of the interior angles of this triangle. We can find angle 8 if we add 71 and 47. Oh, I see that we did that here. We added 71 and 47 here. And here I've completely forgotten that we established as we built this picture that we had a transversal cutting 2 parallel lines. So the very first thing we established was that angle 1 was equivalent to angle 8. So once I found angle 1, I forgot that I knew angle 8. We found that angle 1 was 62 degrees, and so we should have immediately recognized that it was equivalent to angle 8. It turns out that we could have used the triangle angle sum theorem, but we can use the more interesting alternate interior angles theorem. So you could have come at that 2 ways. But I like that more basic understanding, the more primitive drawing that we made that had the Z shape. This was the corner space, if you remember. These were equal. So angle 8, we get to use this cool new toy that we have called the alternate interior angles theorem to show that angle 8 is equal to angle 1. And angle 1 by the triangle angle sum theorem was 62. So angle 8 by the alternate interior angles theorem is also 62. And now all that's left is angle 6, which we don't have any fancy way to find other than to use the triangle angle sum theorem. So we need to add 42 to 109 and subtract that sum from 180. Nine plus 2 is 11. Carry the 1. 1 plus 4 is 5. Plus 1 comes down here. So we have 151 degrees. Let's take that from 180. We'll borrow from the 8, make it a 7. Make the 0 into a 10. 10 minus 1 is 9. And 7 minus 5 is 2. So we have angle 6, finally, to be 29 degrees by the triangle angle sum theorem. Angle 6 is 29 degrees. Thank you so much for your attention.